For the audience, I'm Kushal Fernandes,
Great
principal
to be
here.
here. Thank you.
Yeah, thank you. And I lead a lot of our work in high tech. And so, to the audience, Rima is the Chief Revenue Officer at IonQ, and really cool stuff in terms of quantum computing and really the next frontier of technology. And when we think about kind of the big bets that are going to shape the future of the world, you're certainly at the forefront of all of that. So,
Thank you. It's absolutely exciting to be in this space.
so Rima, when you think about the impact or the potential that quantum computing can generate, where do you see it playing the biggest role?
Yeah, quantum computing is going to have an incredible impact on our world. It's going to solve problems that are super complex and intractable today. If we were able to solve them, we would have solved them on supercomputers. They will be able to help us in a number of areas. One is simulation. Being able to simulate Mother Nature. That is the hardest thing. What we do today is we actually have approximations because we cannot simulate Mother Nature. And actually, this is the reason actually quantum computers were even invented. The scientist, Richard Feynman, he actually said, if you're looking to simulate Mother Nature, Mother Nature is quantum. You better make it quantum mechanical. So trying to simulate Mother Nature in a digital way is super hard, and quantum is the answer. And that's the big aim of quantum computing, is it will help us develop better drugs, it will help us develop better materials, it will help us with carbon capture. We already know that as the quantum computers become larger, we will be able to address a lot of these very, very difficult problems today.
No, that's fantastic. I think, one of the most exciting aspects of this is whenever there's technology, tied to fundamental science, and as you said, you quoted Richard Feynman, and going back to how the world is kind of actually structured and built, it unleashes so much of possibility and capability. So I guess, where have you seen this kind of play out in terms of success stories in the real world?
Yeah, so I'll just give you some examples of what we're doing at IonQ. So we're working with Hyundai, for example, on building better batteries. So EV cars are very popular. Everyone wants EV cars, but the problem is the battery. 40% of the manufacturing cost is from actually manufacturing the battery. And so what we're doing is we're working with them on finding more efficient batteries. That goes back to what I was talking about before, when you start looking at how you can use quantum simulation to build better materials. That's what we're doing with Hyundai, and I expect that we'll be able to do much more as the computers are become larger and more companies are also thinking about problems in a quantum way and are able to build more efficient products using a hybrid approach, using today's AI and the best of what quantum brings, so that you can build the best solutions.
No, that's fantastic. And I think you brought up a point around, thinking in a quantum way.
Yeah.
And that really is not something, that is easy to understand, because
Yeah.
quantum is conventionally been the realm of physicists. And so how do you look at it in terms of challenges that need to be overcome for something like quantum to really create value in the world?
Yeah, I faced that also in the AI space. Like initially, when companies started thinking about AI, they also had to break out the problem differently and understand what AI can bring to the solution, and figure out how they actually introduce it into their workflow. And with quantum, it's the same. It's understanding the capabilities of quantum, what it actually brings to the table that's unique and different, and figuring out what are you not able to get to good results with today, and what are the different areas that you can bring in quantum to actually make the solution that you're building much more effective and better and more accurate. It's understanding both what problems you have, but also what a quantum can bring to the table that can enhance the problem that you're trying to solve.
Great. And I think when you think about that, right, like what is the role of human ingenuity in kind of helping bridge that gap and get, cross the chasm, as it were?
I'm a big believer that AI and quantum is going to give us incredible opportunities, incredible possibilities, and give us solutions that we didn't even think about. And it's going to make us run faster, think about things in much different ways. But we need to still keep a human in the loop because AI can actually look at things and learn from patterns and be able to give us incredible solutions. But you still need the human ingenuity to come up with something totally different. Like, for example, Henry Ford said that if I had asked people what they wanted, they would have told me that they want a faster horse. If you train with the data that we have, we're going to learn different approaches, different ways of combining data, different trends, but coming up with something totally different still is something that a human intelligence brings to the picture. Like Henry Ford came up with a car, which was totally different. But eventually, as we grow these models, eventually we're going to get to a point where we can actually simulate true human intelligence. Today, AI is narrow. As we start combining more and more approaches, we're going to start getting close to AGI. And when we start getting there, then we're going to get close to what humans could do. And today's large language models, quantum computing, and bringing multimodal approaches to the table. These are all the different ways that are going to contribute to helping us get to higher level thinking and becoming more general in the way these AI models can interpret and produce results and ideas.
Yeah, it's both fascinating and I'm not going to lie, a little bit terrifying in terms of what the future holds. And I love the analogy that you gave
Yeah.
of Henry Ford. For people who don't know what quantum computing is all about, is it a faster horse or is it a Model T?
Today, we all know about how digital computing works. You have bits that are either one or zero, and you have to turn everything into a digital approach so that you can process and compute the information. The nice thing about quantum computing is that we use something different. It's called qubits. And what qubits are, they could be in multiple states at the same time. And then you use the properties of quantum mechanics, which are superposition, entanglement, and interference. And using these properties, you're able to actually simulate a nature because you're not having to turn it into a digital process to actually simulate the natural world. And what's really incredible about quantum computing is because you are able to be in multiple states at the same time, you can access a much larger computational space and be able to, in parallel, at the same time, examine so many different possibilities and get results really fast. You can examine all these different possibilities at the same time and come up with an answer.
Yeah, as someone who's actually tried to solve that and write code for it, what's it called, an NP hard problem. So I think, computational power certainly helps there. But, when people think of quantum computing, it probably conjures these images of like, massive warehouses and, you think of a nuclear reactor or something like that. But what does it actually look like and how big is it?
Thank you so much for asking me this question because whenever you open a magazine, you see these dilution refrigerators and you're like, oh, wow, this must take a lot of power. Actually, the approach that we use at IonQ is using natural qubits. So there's two approaches to quantum computing. You can actually create synthetic qubits, and that requires dilution refrigerators. We use natural qubits. So what we do is we take an atom, we zap it with a laser and create an ion. And once we create an ion, we actually why don't I show you?
That's great.
A trap.
That's it. It fits in this box.
Yes, that is a trap. And so what we do is we actually hold these ions here on top of the strap, and then we perform the operations using a laser.
Wow.
And it's rack mountable, and a data center uses much less energy than you would need in a data center. And quantum computing is going to be a savior, in my opinion, for continuing to be able to use AI and quantum AI to solve some of these biggest problems. Because what's happening today is AI is super powerful, but it needs a lot of power. And the estimates are that by 2030, 25 to 30% of the power grid will be used by data centers in the US. Using a quantum computer with classical computers to take the tasks that are very compute intensive and put them on a quantum computer, we expect will help with this power problem and allow us to still build these hybrid algorithms that are very powerful but take some of the very compute intensive operations that quantum is good for,
Yeah.
which are optimization, simulation, and quantum machine learning, and run them on a quantum computer, and then be able to have great results and a great application that gives you the outcomes that you are looking for. Another area is optimization. And the problem is because as the variables become much larger, you don't have enough memory to test out all the different approaches. For example, like the traveling salesperson. And so what a quantum computer could do is it actually can examine all the possibilities at the same time. You just have to have enough qubits, because what you could do is 2 to the power of qubits that you have, that's the computational space that's available to you. So you can actually examine all that space at the same time and get the results right away. And the third area is quantum machine learning. And with quantum machine learning, we expect it to work hand in hand with today's AI that runs on classical machines. Quantum computing is not good at everything. So what we would do is we would take the things that the quantum computer is very good at and move them to the quantum computer while continuing to run the rest of the operations on a classical machine. And the results will go back to the classical machine and vice versa. And so we expect a lot of these applications will be hybrid applications. But what's really great about quantum machine learning is it excels at a number of things. It's much more efficient. It means less operations to generalize. And if you have a sparse data set, for example, it will generalize more quickly, so you need less data. Also, it's really great at pulling the insights from the data, so you learn new things. And especially if there are rare events, it's very good at pulling those nuances from the data.
Oh, that's fantastic. I think, one of the thoughts that comes to my mind, you described is this is really a win-win. You get performance on one side, unprecedented performance, and on the other side is good for the planet, less energy consumption. If you think about what are the barriers to adoption, like what are we waiting for to make this scalable and, the way we compute in the future?
You know what? You're spot on what you said. It's win-win, and we expect it to be an and. It's not going to replace anything we're doing today. Today, AI and classical computing is going to continue to grow and be more powerful and be able to generate even better and better results. This is an and. It will help us do things that we're not able to do today in a faster, more efficient way. So what we're waiting for is we're in the early days of quantum computing. Today, we're in the NISQ era. So we're able to prove out a lot of these algorithms and show the value that they will bring. But for us to solve the really big intractable problems, the quantum computers need to be larger. And we have a roadmap to get there. So it's what we tell our customers is, it's important to work on the problems and the algorithms today, because it takes time to build applications. We all know if you're building something that you expect to take to market in 2 years, you need to be building it now. So we expect that in 2 years we'll be able to have applications that bring real benefit and real commercial advantage to our customers. So today we will prove it out at a smaller scale, and we'll continue to build on it and expect to have real commercial results in the next 18 to 24 months for some applications. But so what we're waiting for is just continuing to build stronger and more powerful machines, and to start integrating them into the current application workflow.
Terrific. Well, I for one can't wait to see that.